Good morning. Assalamualaikum. Today is my lecture 7 of CHM 577. Yes. So today I'm going to talk about hybridization of atomic orbitals. And the lecture that I'm giving today, the notes have been prepared, the slides have been prepared by Dr. Amalina, the resource person, and I'm presenting it for my students with some additional notes that I have added. So, uh, as an outline, I'm going to do a little bit of revision of shapes of atomic orbitals. I understand that you have learned about shapes of atomic orbitals during your matriculation days. Um, you're going to be needing that for this lesson. So I do a small recap with you. And I'm going to introduce to you some limitations of the valence bond theory that you have learned in my previous lecture. And that leads us into hybridization. And these three topics are going to be covered in lecture 7, whereas the other two topics, which are mode of orbital overlap and types of covalent bonds, as well as molecular orbital theory and electron delocalization, will be covered in lecture 8. Right, let's do some recap on the shapes of atomic orbitals. I'm sure you recall these diagrams. S orbitals have the shape of a sphere, yes, spherical shape, and as orbital, for each one there is only one orbital. When we move on to the p orbitals, the general shape of p orbitals are like a dumbbell, that exercise thing that people are using, where it has a middle, and then there are lobes on the left and the right hand side of that. So these p orbitals have shapes like dumbbells, and the p orbitals are made up of a set of 3. So you have px, py, and pz, where px is lying, the lobes of the dumbbell in here, yeah, the lobe of this dumbbell is lying on the x orbital, no, x-axis, I'm sorry. And then you have your py, where the lobes of the dumbbell are lying on the y-axis, and similarly the pz, you have the lobes lying on the z-axis. So when you are combining all these px and py and pz, putting the atom right in the middle, you are going to have them uh, perpendicular to each other. The x, the px, and put this z here, the pz, and then the py, they are actually making some kind of an octahedral looking shape, yeah, they're perpendicular to one another. So p orbitals are dumbbell shapes, and there are 3 orbitals, set of 3. Whereas your d orbitals, the set is 5 orbitals in each of the d set. So you have uh, dxy, dxz, dyz, dx squared minus y squared, and dz squared. And the dxy, dxz, and dyz, they are having the lobes, or all of these, they have shape a little, all of them are shaped like butterfly. They have four lobes, but the difference is the xy, xz, and yz, the lobes are situated in between the axes. So the dxy have the lobes located between the axis of x and the axis of y, whereas the xz between the axis of x, obviously, Z and X, I'm sorry, X and Z, whereas the YZ is between the axis of Y and Z. So that is you having the general shape where the lobes are located in between the axis, not on the axis. The difference with that x squared minus y squared and z squared that the lobes are located on the axis, not between the axis. So that's a quick recap of the shapes of orbitals of S, of P, and of D orbitals. Okay, so I'm going to uh, introduce to you the limitation of valence bond theory. Now, valence bond theory is saying that bonds are formed by the sharing of electrons through the overlapping of atomic orbitals. So when bonds are to be formed, the atomic orbitals will overlap. They will overlap like that. And then through this overlap, bonds are being formed. So it's really quite simple. You have one atom moving from here to there, another atom, and when the uh, orbitals are overlapping like so, yeah, they are overlapping like that. Upon overlap, you have bonds being formed. Contohnya, for example, if you have carbon with hydrogen, yeah, the orbital of hydrogen overlaps with the orbital of carbon, and you get the carbon to hydrogen bond being formed. That is what the valence bond theory is saying, and to a large extent that is quite correct. However, there is some problem that is encountered when we apply valence bond theory to ammonia, for example. Now, everybody knows that ammonia is NH3. There are three NH bonds, and these three NH bonds, we can imagine that they are being formed through the overlap of the s orbital of the hydrogen with the p orbital of the nitrogen, because we all know that nitrogen is 1s2, 2s2, and 2p6. This is the 1s2 electrons. These are the 2s2 electrons, and the black arrow pointing upwards are the 2p3 electrons. So if we imagine that these are paired up, so nothing can happen to it. These two are also paired up, so nothing can happen to it as well. So you can see that the p electrons are single. 1, 2, and 3. So that's perfect. So when there are three hydrogens coming, we are saying that the hydrogen orbital will be overlapping with the nitrogen p orbital, and they're going to make a bond. So if you imagine that this is your px, that is your py, and that is your pz, if on each of these orbitals there is one orbital of hydrogen coming in and overlapping itself, what we are going to imagine is that the NH bond to another NH bond, we will have a 90-degree angle, because from, for example, if you're taking this lobe with one hydrogen, with one hydrogen, and that lobe with hydrogen at the bottom, and this lobe with hydrogen on the left. So when you combine them, you're going to be able to see that through the prediction. Oh, I'm sorry, this is not moving well. Through the prediction, we are saying that the three 2p orbitals with bond angles of 90 degrees to each other, they're going to make hydrogen angle to be 90 degrees, according to the valence bond theory. But in actual fact, experimentally, it has been found that the H and H bond angle is not 90, but it is actually 107.3, which is very, very different from what we predict it's going to be. So there must be something else going on that we need to venture into when you want to explain the angle of 107.3 in ammonia instead of the 90 degrees that we expect. So that new something, that new approach is called hybridization. Hybridization really mixing, mixing of atomic orbitals. So the S is mixing with the P, so to speak. So that is the limitation of valence bond theory, and I'm going to introduce to you the concept of hybridization of atomic orbitals so that you could um, predict correctly uh, the shape or the bond angles in ammonia, for example. Now, what is hybridization? Hybridization is the mixing of two or more atomic orbitals to form a new set of hybrid orbitals. So you have the atomic orbitals are the s orbital, the p orbitals, and the d orbitals. So these are atomic orbitals. When they mix with each other, they are going to form a new set of orbitals, and that set of orbitals, we call them hybrid orbitals. Yeah. There are two things about hybridization that you need to remember, that the number of hybrid orbitals that you obtain is equal to the number of atomic orbitals that you mix in the beginning. So for example, if you're mixing one s orbital with one p orbital, you are going to have two sp orbitals. Yeah? So one atomic orbital s, one atomic orbital p, you mix them up, what you're going to get are two sp hybrid orbitals. So that's the first rule. Now the second rule is the type of hybrid orbitals that you will obtain vary with the type of orbitals being mixed. Obviously, when you mix different atomic orbitals, you're going to get different hybrid orbitals. So the analogy of hybridization is when you mix blue with yellow, you're going to get green. So you are mixing the primary color of blue with a primary color of yellow, you're going to get a derived color of green. So what will you get when you mix, for example, blue with red? Blue with red, you don't get green, you're going to get purple. So similar with this hybridization of atomic orbitals. Yeah. So for this lecture, I'm going to cover the formation of 5 hybrid orbitals, which are sp hybrid orbital, sp2 hybrid orbital, sp3, sp3d, and sp3d2 hybrid orbitals. So let's go through it one by one. Let's go through the formation of sp hybrid orbital of beryllium in the gaseous beryllium chloride. So it is always the central atom that is being hybridized, the atomic orbital of the central atom that is being hybridized, not the chlorine. The chlorine in this case is not hybridized. Yeah, we're not going to talk about the hybridization of chlorine. We're going to talk about the hybridization of the central atom of this molecule, beryllium chloride. So for beryllium, Be is, I'm going to go here. Yeah, beryllium, it has electron configuration of 1s2 to s2. Is that right? Yes? Beryllium has an electron configuration of 1s2 to s2 or helium to s2. That means in the valence shell, in the outermost shell, there are two s electrons in beryllium. So you have the 2s orbital here, and you have the 2p, 2px, 2py, and 2pz. So in beryllium chloride, the hybridization that's going to happen is the mixing of your s orbital with one of the p orbitals. There are 3 p orbitals, but not all p orbitals in here are going to be hybridized, are going to be mixed with s, only one. So when you are mixing s orbital with your 2px, for example, yeah, this is your s orbital, that is your 2px orbital. What you're going to be getting, you mix the shape is, if you can imagine, this is the left-hand lobe is originally the S, and then the tiny little P lobe here. Yeah. So you have S, P, S, P. So one S orbital with one P orbital will produce two sp orbitals. Yeah. S plus P makes sp plus sp. So this is the shape of one sp orbital, and that is the shape of another sp orbital. But you imagine that this is happening on one atom beryllium. So this is one and that's another. When you combine, it will look like this. And when we simplify the shape, you are going to have a shape like this. So that is one sp orbital, that is another sp orbital, and they are making a good linear shape. Maybe if you don't understand this at this moment, don't worry. As we go along to the different hybridization, you're going to see the trend. So this is a shape of that sp orbital. It is a linear geometry. Just leave it there for a while. I'm going to talk about the energy level diagram of sp hybridization. Now, of course, you know your 2s is located at a lower energy level compared to your 2p. Yeah, 2s is lower in energy level compared to your 2p orbitals. Now, this is S and px, py, and pz. So for beryllium to make sp orbital hybridization, only this s and that p are going to mix, whereas this py and that pz, they are going to remain unhybridized or unmixed. So the 2py and the 2pz will not change the energy level. Nothing happens to them because it's not mixing with anything. So this is your 2py, that is your 2pz. But what happens to these two orbitals that have combined or that have mixed or that have hybridized? So when S and PX mix, mixing, you're going to get two sp, like the one that I explained previously. This is one sp, that is one sp. But where do they occur in terms of energy level? They will be existing in an energy level higher than S but lower than P. But they still are in the same energy level. This sp and that sp, they are still in the same energy level with each other, but this location is in between S, this is your original S, in between S and P. It is right here in the middle. So that is the hybridized beryllium atom in the sp manner, sp hybrid orbital. So when the hybrid orbitals have been formed, the sp hybrid orbitals have been formed, these two electrons, because we know that beryllium has two valence electrons, so each one of these electrons will be occupying this sp on the left and another one, this sp on the right. So each one of these hybrid orbital will have one electron sitting in it. There you are. This is a repeat of what had been explained. S and Px making Sp and Sp, mixing of these two Sp orbital will give a linear shape. This Py and Pz will remain unchanged. So when you combine this 1, 2, 3, and 4, what you're going to get is this thing at the bottom. Can you see it? Oops, excuse me. What you're going to see is this thing at the bottom. This beryllium right there in the middle. This is your Sp hybrid orbital on the left. That is your Sp hybrid orbital on the right. This one that is from top to bottom, that's your 2pz unhybridized. And the other one is this one here. It is actually your 2py unhybridized. And I was telling you that the electrons will stay at the orbital that has the lowest energy level. Let's have a look at this one here. And the lowest energy level actually is the Sp and the Sp. The electrons will not go and stay in the 2py or the 2pz because these have the higher energy level. So these two electrons will one each occupy this Sp hybrid orbital and that Sp hybrid orbital. Now, what happens next is really quite fascinating. So this singly occupied Sp hybrid orbital, when a chlorine atom approaches it, when a chlorine atom approaches it, this single electron in the chlorine atom, if you can recall, chlorine is uh, P5, P5, S2P5. So in the P5, you're going to have two paired up, another two paired up, and that's one unpaired. So this is the unpaired electron of the chlorine. It's going to pair up with this unpaired electron in the Sp orbital. And it's going to make a bond. So it's going to overlap this chlorine orbital is going to overlap with that Sp orbital, and this one, this chlorine on the right, is going to overlap with that Sp orbital on the right, and you're going to get two bonds of BeCl. There's one bond on the left of your beryllium, you get BeCl there, through the overlap of these two orbitals, making the two electrons pairing up with one another, and similarly happening on the right of the molecule. So this is what you get. This is, let me make that bigger so you can, so yeah, yep. You get to see that this chlorine is, oh, second, oh, it's running all over the place. You get to see that this chlorine is overlapping with that Sp, making beryllium chloride and another beryllium chloride. So the Cl, Be, Cl bond angle is 180 degrees, and you get a linear molecule. Yep, you get a linear molecule, and linear molecule is always associated with Sp hybridization. Well, almost always. You're going to see some exceptions later. So bear with me that this is the basic fundamental mechanism of hybridization. Again, I'm going to have to repeat to you that the unhybridized atomic orbital does not have change in energy level, whereas the hybridized orbitals will have a changed energy level. It's going to be higher than the 2s and lower than the 2p. Yeah, so this is your Sp hybridized beryllium, which is this one. And This is your isolated, unhybridized yet. Yeah. So that is the first example of hybridization of sp. Now, to make your understanding stronger for hybridization, I'm going to go ahead and talk about sp2 hybridization. Now, can you have a guess? How are you going to get sp2 hybridization? What orbitals are you going to mix to get sp2 hybridization? So the answer is really very, very simple. You're mixing one s orbital with two p orbitals. So you have Sp2 hybrid orbital. So this is it. We take example of BF3, boron trifluoride. So we want to see the sp2 hybrid orbital of boron. Now, if you are watching this lecture and also following it through with the notes that you downloaded from UFuture, you're going to see that what I am showing you in this slide or in the previous slide have a lot more information than your downloaded PDF lecture. So please write on those notes, add on what I have um, added into my notes so you can follow my lecture and get some engagement between your eyes and your hand and your thinking brain. Right, so let's have a look at the sp2 hybrid orbitals of boron in BF3. Now, this is your boron. Yep, I'm going to take this boron. Oh, let me see. Yep, that's your boron, and boron has a electron configuration of helium 2s1 2p1. Sorry, 2s2 2s2 2p1. So that's your 2s2, that's your 2p1. And for for your BF3, you are getting three bonds, obviously. One BF, another BF, and another BF. You're getting three bonds. So you cannot have sp hybrid orbital because sp will only give you two bonds. So you need to have three bonds. So to do that, you are mixing S and 2p. And repeat of what I had explained, the unhybridized 2pz will have its energy not changed, whereas the hybridized S and the 2p's making sp2 will have the energy level change, which is lower than 2p and higher than 2s. This is the sp2 hybrid orbital, and if you are looking at the shape, you are going to get a trigonal planar shape. I don't know whether it's not shown here. No, it's not shown here. So just believe me, if you go through this same procedure or that same procedure like this, you are going to end up with the drawing of sp2 to be trigonal planar. So you have your sp2, three of them, 1 and 2 and 3, and then you have your unhybridized 2p. Yeah, this is your unhybridized 2p, and each one of these sp2 are going to accommodate one each of these electrons of boron. So one of these electron is from boron and another one is from fluorine. They pair up, they make a bond between boron and fluorine. Similarly happening here. Yep. And similarly happening there. So you have BF3, the shape of which is trigonal planar. Remember, your SP is linear, your SP2 is trigonal planar. So that is the rule. That is the rule. Sp2 is always having the geometry of trigonal planar, whereas Sp will always have the geometry of linear. Yep. Now, this is the formation of BF3. through the hybridization of your boron into sp2 and then the pairing up of the single electrons from fluorine to boron, making 3BF bonds. Yeah, trigonal planar. Now, next we go into the sp3 hybrid orbitals of carbon in methane. Now, carbon is helium 2s2, 2p2. Yeah, 2s2, 2p2. Now, when you look at methane, CH4, obviously you see that there has to be 4 bonds, obviously. CH, 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 and CH. So you have 4 CH bonds. And to get 4 hybrid orbitals, you need to mix 4 atomic orbitals. It has to be S with the 2px, 2py, and 2pz. So the S with these orbitals of p, they're going to make hybridization, and they're going to form, because initially you start with 4 atomic orbitals, 1, 2, 3, 4. You are going to then have 4 hybrid orbitals, like the rule that I mentioned earlier. So sp3, 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 and sp3. So 4 sp3 hybrid orbitals, and when you combine them, you're going to get the shape of tetrahedron, and there is no unhybridized atomic orbital. Yep, because this is also, despite being empty, it is also getting involved in the hybridization. So you have sp3. Now remember, sp3 will always be tetrahedral. Okay, repeat. What about the linear? What is the hybridization of a linear geometry? I hope you answer SP. What is the hybridization of a trigonal planar geometry? It is sp2. What about sp3? What is the shape or what is the geometry of sp3? It is always tetrahedral. And it is tetrahedral for methane because for methane you have 4 bonding pairs of electrons. How do we know we have 4 bonding pairs of electrons? Go back to your Lewis diagram. Remember Lewis diagram? So for methane you have 4 electrons, 4 valence electrons of carbon. So the first one pair up with hydrogen, the second, the third, and the fourth also. You get 4 bonded pairs of electrons. So you get tetrahedral. And tetrahedral, the hybridization that is associated with tetrahedral is sp3. Remember that. Yeah. Then I'm going to go next into sp3 also, but not in methane, but in ammonia. When you recall that we have learned previously through VSEPR that ammonia, it has one pair of lone electrons and then 3 pairs of bonded electrons. Yeah. So how are we going to explain that using hybridization? So try to draw your nitrogen valence electrons. Yeah. So nitrogen is 2s2, 2p3, 2s2, 2p3, 1, 2, 3. And you are mixing all these orbitals. You're mixing all these orbitals to make 4 sp3 hybrid orbitals. But you have 5 electrons to distribute in these 4 hybrid orbitals. So when you put 1, 2, 3, 4, the 5th one has to come in and pair up with the first. And this is that lone pair of electrons on nitrogen. The other 3 electrons are single and doesn't have a pair. So if you put sp3, and sp3, as I was telling you, is always tetrahedral. So you are drawing the shape of nitrogen with 4 sp3 hybrid orbitals around it. You put one lone pair there, which is this one here. And then 3 hydrogens are pairing up with the electrons each of these single electrons. So you have nitrogen, hydrogen, 1 bond, second bond of nitrogen, hydrogen, and the third bond of nitrogen, hydrogen. So it is sp3. The original shape is tetrahedral, but imagine that this, of course, is the lone pair, and it is invisible. It is not seen. So if you imagine that this is invisible, what you get is actually tetrahedron that doesn't have the summit of the top here. So it is actually trigonal pyramidal. And for tetrahedron, if you recall our VSEPR, an ideal tetrahedral has a shape, has a bond angle of 109.5, but because the lone pair is pushing the bonded pair further away, so that is going to make this H and H bond angle to be narrower, smaller than 109.5, and it becomes 107. And that explains why in ammonia you do not get a perpendicular. You do not get a 90-degree H and H bond angle, but you get 107. So that is the explanation. You use hybridization theory to explain the bond angle of ammonia. So you have for your ammonia where you have 3 bonding pairs of electrons and 1 lone pair of electrons, the shape will be trigonal pyramidal. Yeah, I hope that is clear. And next, I'm going to talk about the sp3 hybrid orbital of oxygen in water. The same story goes. We start with if oxygen, you have 6, yeah? 2s2, 2p4, 6 valence electrons, 2, 4, 5, and 6. So you are hybridizing the s and the 3p's. You get 4 sp3, 1, 2, 3, 4, 4 sp3 hybrid orbitals. When you arrange the electrons in those hybrid orbitals, you end up with 2 lone pairs of electrons and 2 singly occupied, and these single electrons are ready to pair up with 2 hydrogens. So hydrogen with oxygen, hydrogen bring 1 electron, pairing up with that one you make HO, and this hydrogen bring 1 electron, pairing up with the second unpaired electron, you get another HO. So that's your water. Yeah, 2 OH bonds, and you have 2 bonding pairs and 2 lone pairs, and these 2 lone pairs are invisible. They are invisible. So when they are invisible, what you get to see are only this bent shape, HOH. That is a bent shape or a V shape. So that is 3 cases of sp3 hybrid orbitals. The first one is the methane, where you have tetrahedron. Where you have all the 4 bonding pairs. The second one, you have your ammonia, where you have 3 bonding pairs, 1 lone pair, where the shape is trigonal planar, trigonal pyramidal. And then the third one is also sp3 hybrid water. Yep, this is your water, sp3 also, but 2 lone pairs that are invisible, so you only get to see a bent shape. Hope that is clear to you. Next, I'm going to talk about the sp3d hybrid orbitals of phosphorus in PCl5. Now remember, when you want to involve d orbitals in your hybridization, it has to be for atoms that are located in the third shell, because there are no d orbitals in the first shell or in the second shell. So it is impossible for elements that are located in the first shell and the second shell to have dehybridization. Only start having the dehybridization on the third shell onwards. So we start with phosphorus. Nitrogen, which is just above phosphorus in the periodic table, will not be able to make this hybridization, but phosphorus will. Because phosphorus is 3s2, 3p3, but there are d orbitals that have not got any electrons. So I'm just putting it in gray here. So your d is there, but it is empty. So 3s2, 3p3, 1, 2, and 3. And you are wanting to determine the shape of PCl5. You see here there are 5 bonds. It is impossible for you to have 5 bonds if you do not involve the d orbital. So you have to mix s, 3 of the p's, and the 5th one is only 1 needed of the d orbital. So you are mixing the s, the 3 p's, and the 1d. You making sp3d orbitals, 5 of them, 5 sp3d orbitals. And you are going to get the shape of trigonal bipyramidal. If you remember the VSEPR, when you have 5 bonds arranging themselves around one central atom, is going to make a trigonal bipyramidal. And these 5 sp3d hybrid orbitals are going to be singly occupied by these 5 electrons, and the 5 electrons of phosphorus are going to each one pair up with the electron from chlorine, 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 and chlorine to make 5 PCl bonds, and the shape of PCl5 is trigonal bipyramidal, and the hybridization associated with trigonal bipyramidal is sp3d. Yep, sp3, not yet enough 5, d. Yeah, so 5 of them. And the next one I'm going to talk about is your sp3d2 hybrid orbitals of sulfur in SF6. The same story goes. Your sulfur is 3s2, 3p4, which is 3s2, 3p1, 2, 3, and 4 there. And to get 6 bonds, you need to mix S with the 3 p's and 2 of the d's. You need 2 more. So because 1, 2, 3, 4, 5, and 6. So it's sp3d2, and the unhybridized orbitals, the 3dx, the 3dy, and the 3d, 3d, 3dxy, 3dyz, 3dxz will have energy not changed because they do not get hybridized. Only these 6 orbitals will have a different energy level, which is higher than the S, a little bit higher than the P, but lower than the D energy level. Yeah, lower than the D energy level, but higher than the S and the P, yeah, orbital. And when you recall your VSEPR, making 6 of these to arrange themselves in space, they are going to produce octahedral, and octahedral shape is associated with the hybridization of sp3d2. Yeah, sp3d2. Yeah, I can see my face. There are 6 hybridization, and each of these electrons are going to then pair up with the electrons from the fluorine and making 6 bonds as F. 6 SF bonds, and in the end, you're going to get octahedral SF6. Yep. I hope that is clear. So I have explained to you 5 types of hybridization. The sp hybridization, which is a linear, the sp2 hybridization, which is a trigonal planar, the sp3 hybridization, the basic of which is tetrahedral, but you can have tetrahedral, you can also have trigonal pyramidal for ammonia, and you can also have bent or V-shaped for water. And then the fourth hybridization that I talked about was sp3d for trigonal bipyramidal, and the last one was sp3d2 for octahedral shape. Right? So this is the summary. When you mix one S with P, you get sp hybridization, and there are 2 hybrid orbitals. You get linear. Example, BeCl2. This is a recap. When you mix S with P, you get sp2. There are 3 hybrid orbitals. You get this shape, which is called trigonal planar. When you are mixing with S with 3 P's, you get sp3, and there are 4 hybrid orbitals of sp3, so you get tetrahedral. And when you're mixing the S with P, 3 of them, and D, you get sp3d, and 5 of those hybrid orbital of sp3d, you get the shape of trigonal bipyramidal, example of which is PCl5. And then lastly, you're mixing 1 of the s orbitals, 3 of the p orbitals, and 2 of the d orbitals to make sp3d2. And there are 6 of them. And when you combine them together, you get octahedral, and the example is SF6. Right. Now, this is how do you predict the hybridization of the central atom of your molecule, the central atom. So the central atom is always the what is in Lewis, the least electronegative. Yeah. Okay. For you to determine the hybridization of the central atom, you need to determine how many lone pairs of electrons and how many bonded atoms. So number of lone pair of electrons, you add it to the number of bonded atom, you are going to either have number 2, 3, 4, 5, or 6. So when you have the lone pair of electron plus bonded is 2, and it can be 0 plus 2, it can be 1 plus 1. Then hybridization is sp. If you have lone pair plus bonded makes 3 count or 3 pairs is sp2. When you have 4 pairs is sp3, 5 pairs is sp3d, and 6 pairs is sp3d2. And the shape, this is linear, that is square planar, not square planar, trigonal planar, that is tetrahedral, that is trigonal bipyramidal, and that is octahedral. So I'm going to stop my lecture 7 up to this point. When I see you next in my lecture 8, we're going to talk about this one. But that is the end of my lecture 7. It's already about 49 minutes now. This is a good enough length to stop. So I hope you understand about hybridization, and it's going to come in handy in our next discussion. So goodbye, everyone. Thank you for listening, and hope you have a good week. Okay, thank you. Bye-bye. Assalamualaikum.